Hi guys, welcome to lesson 10.5 for Algebra 1. Today we're going to be talking about graphing square root functions. Our objective for this lesson is to learn how to graph square root functions, so a new shape for you guys that you guys may not have seen before, and also how to translate graphs of square root functions, which is super easy because if you guys remember, translate just means to move left, right, up, or down. All right, so this one could be a pretty easy lesson, but before we go into how to graph square root functions, let's do a little bit of a review on just different function shapes that we've talked about already. In order to help us out with our review of different function shapes, let's go ahead and get our good friend Desmos back out here. Hey yo Desmos, where you at? Here I am, dog. All right, let's go ahead and start graphing. Alright, on the screen for you, I have an example of what's called a linear function. A linear function. This red line is represented by the function y is equal to 3x plus 5. How could we tell that this guy is supposed to be linear? Well, one, it has a regular x and not a fancy x. And if we try to graph this, it would have a y-intercept of 5 and a slope of 3, up 1, 2, 3, over 1, up 3, right 1, up 3, right 1, and I have this line. Cool. So this is a linear function. Next on the list of past functions that we've talked about, we have this guy called an absolute value function. Anybody have any idea what shape this is going to be? Or maybe I should say what it's going to be? Well, that's right. This is going to be a V-shaped graph. A V-shaped graph. Absolute value will always be a V-shaped graph. And remember, with these types of functions, if we added something at the end, like let's say I add 2 at the end, it moved up 2. It moved up 2. There we go. If I went ahead and added 3 at the end, it would go up 3. And if I subtracted 3, it would go down 3 overall. What would happen if I put a negative sign in front? Well, it would go ahead and flip. And what would happen if I put a value bigger than 1 in front? Well, it's going to stretch. And what would happen if I put a value less than 1, like let's say 0.5, it's going to compress. It's going to flatten or widen out a little bit. All right, cool. That's a good review for us, at least with absolute value graphs. Next, I have this graph, and this graph is called an exponential graph. Anybody remember what type of shape this is going to be? Correct. This is going to be skateboard ramp. If you guys remember, exponential graphs, they make what we call skateboard ramps. We read graphs from left to right, just like we read English from left to right. From left to right, this thing is growing, and we would call this exponential growth. Okay? What would happen if the number, or just kind of a recap for us, that this number right here acted like our y-intercept, so in this case, positive 3, and what would happen if we put a number less than 1 next to the x? Well, that became exponential decay. Growth, decay, growth, decay, growth, decay, growth, decay. Da, 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 da. All right, you guys have probably seen that enough this year. All right, the last function that we learned about was something called a quadratic function. Who can tell me what shape this would be? Grace. Good job, Grace. Good job, Grace. Grace correctly identified that this would be a quadratic shape or a parabola, meaning a U-shape graph. And if I had something like plus 2, the vertex moved up 2. If I had something like minus 2, it moved down 2. If I had something like a negative sign in front, it flipped. Okay, so these are all very similar rules that actually do translate from one function to the next. And this is an example of our parent function. All right, cool. Are y'all ready for this next new graph that we're going to talk about? Something called square root graphs? Well, here it is. Ready or not, here it is. All right, this is an example of our square root function. This is the parent function for y is equal to the square root of x, also called a square root function. Now, this is the shape that we're going to go ahead. So what I'm going to do is I'm just going to drag this over because you notice that this one, not so symmetrical. With our quadratic, it was pretty symmetrical. All right, with our absolute value, pretty symmetrical. All right, but with this guy, not as symmetrical. This guy has a clear starting point, and it kind of moves over. And then, you know how I had like nicknames for all the different shapes? This guy is what I affectionately call the North Korean missile. Starting at one point, the missile is launched this way, whichever land may be going, towards the right, right? And it continues to go off in that pattern. All right, so this is what I affectionately call the North Korean missile. Now, again, these are all just dumb little nicknames to help us remember what the general shape is. And really, this really does help. All right, just kind of keep this in mind. Starting at one point, and it goes off in another direction. All right, cool. Now, what I want to stress with all types of graphs is that there's a pattern that we should be following. And when we had a quadratic function, we did have a pattern. We went up 1, over 1, or over 1, up 1, over 2, up 2 squared, over 3, up 3 squared, right? Because we followed a pattern of the square. Now we're going to follow a similar pattern for our square root. All right, let's go ahead and take a closer look at how this might work, how this function might actually function. Now I've copied a picture of our graph from Desmos and put it onto this blank screen. And you know me, I'm not the biggest fan of tables, but tables are very helpful, especially when we're just learning about new function shapes. And for this picture right here, we do have a new function shape. All right, so I went ahead and made a table with a few different values to plug in. For our x values, I picked some very specific numbers, and hopefully we'll understand why I picked these numbers and which numbers we should be picking for square root functions. All right, let's go ahead and start with 1. If I move over, starting from this point, moving over in the x direction 1, I'm supposed to go up the square root of 1. When I plug in my x value into my function, the square root of 1 is 1. That means that I have a point right here at 1, 1. Cool? Now, we could try the same thing with 2. If I went over 2, I would go up the square root of 2. The issue is the square root of 2 is not a number that we readily just know off the top of our head. Not everybody. All right? Maybe an easier number to use instead of 2 or 3, because the square root of 3 would have the same issue as the square root of 4. If I went over 1, 2, 3, 4, I'm supposed to go up from here the square root of 4. The square root of 4 is 2. And look at that. It ended up right on the corner of our graph. Maybe that's a coincidence. If we try the square root of 5, square root of 5 wouldn't be that nice. Square root of 6, not that nice. The square root of 7, don't really know. The square root of 8, nah. But what about the square root of 9? If I moved over the square root of 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. If I went over 9, I'm supposed to go up the square root of 9, and the square root of 9 is just 3. And look at that. It ends up right there on the corner of our graph. So what I'm doing is I'm picking numbers that are considered perfect. That's a terrible way to write it. Perfect squares. I'm picking my perfect squares, numbers that I know that when I square root them, they're perfectly going to give us a whole number, and we're going to plot those. All right, so the next perfect square would be 16. If I went over 16, I'm supposed to go up the square root of 16, which is 4. 1, 2, 3, 4, and I have another point. So this is the pattern. Just like when we had quadratics, if I went over 1, I went up 1 squared, over 2, up 2 squared. Now we're going to use square root. If I go over 1, I'm going to go up the square root of 1. Over 4, up the square root of 4. Over 9, up the square root of 9. Over 16, up the square root of 16. And for these values, I just want to be very conscious of the numbers I pick. If I'm going to be doing this by hand, I just want to be very careful with the numbers that I pick. Back to our lesson, you can see that with this function, we would want to be very careful about the numbers that we pick. Picking square root over 1 up to square root of 1 over 4 up to square root of 4, these are going to be very valuable for us when we're trying to plot out what numbers to use for our graph. All right. Now let's go ahead and talk about how to find the domain of a square root function. Now here is a graph of our parent function, y is equal to the square root of x. Now, we want to go ahead and figure out what are the values of the domain of this function. If you remember, domain referred to the x values of the graph, and the range referred to the y values of the graph. So what are the values of the domain? Well, looking at this, we would say that on our x-axis, this is our x-axis, starting at 0, all right, it looks like it's every value that's greater than 0. All these values, everything on this side of 0 counts. So for this specific graph, we would say the domain is x is greater than or equal to 0. For the basic fact that this guy right here is a starting point and everything equal or greater to it is in our domain. For this graph, you can see that our vertex moved from 0 to 5, and because it starts at 5, you can say that the domain is going to be x is greater than or equal to 5. For the basic fact that starting at 5, anything that's greater than or equal to it in the x direction has a value that can reach up and touch our graph. Any number greater than 5 has an x value that is associated with it. This new graph would have a new domain value that would be x is less than or equal to 10, because every number less than 10 has an x value associated that can reach up and touch the graph, but nothing greater than 10 has that value. So this is the graphical representation of what a domain should look like for this type of problem. Mathematically, it's actually pretty easy to figure out what the domain of this function is going to be. In order to find the domain of this function, the only thing that we really need to worry about is the inside of this thing, which is known as the radicand. If I just take this inside of the square root, in this case it is 3x minus 9, and I say it's greater than or equal to 0, right? I can just solve for x and find my domain. Right? So how would I get x by itself? Well, what I would do is I would add 9 on both sides, plus 9. I have 3x is greater than or equal to 9. Divide by 3 on both sides. And then I would get x is greater than or equal to 3. And this would be the domain of this function. Right? What we are doing is we're basically just taking our radicand and setting it greater than or equal to 0. Why? Well, we know that this is a square root, and we cannot find the square root of a negative number. It has to be greater than or equal to 0. So let's go ahead and do another example. Like this one right here, the radicand is just negative 2x plus 5. In order to find the domain, we're just going to set it greater than or equal to 0, and then we're just going to go ahead and solve for x. I'm going to subtract 5 on both sides, negative 2 or equal to negative 5. Then you divide by negative 2 on both sides, and I get x is less than or equal to 5 over 2. Now, why is it less than or equal to? We started off with greater than or equal to, but all of a sudden this thing flipped. Well, notice we divided both sides by a negative number. When you divide both sides by the negative number, that sign gonna flip. So let's go ahead and practice a problem kind of similar to something you might see on your homework if we had to graph these guys. Well, alright, let's go ahead and say f of x is equal to 2 times the square root of x. Now a reminder that f of x is just the same thing, it's just function notation. It means the same, messed that one up. Means the same thing as y. Alright, so we can go ahead and say that this is the same thing as y is equal to 2 times the square root of x. If I was asked to graph this guy, I would want to pick values of x that are going to be easy to plug in, and specifically, we want them to be perfect square values. For your graph, I want you guys to plot 3 points that plug in, and to make it easier, why don't we go ahead and allow 0 to be one of those points. So this would be 2 times the square root of 0. The square root of 0 is 0. 0 times 2 is 0. So this would be 0, 0. So one point that we can graph is a point 0, 0. All right. Let's pick another perfect square. An easy perfect square that I could think of is 1. So 2 times the square root of 1 is just going to be 2. So if I try to graph x is our 1, our y should be 2. Now this should go over 1 in the x and up 2, so I should have a point here. Now notice we're multiplying everything by 2, so these numbers can get pretty big pretty quickly. So we want to be careful with the numbers we pick. We want to pick numbers that are going to be reasonably small and that they can try to fit in our graph. Let's pick one more perfect square. An easy perfect square for us to work with is 4. So this is 2 times the square root of 4, which is the same thing as 2 times 2, which is just going to be 4. So this would have a point at 1, 2, 3, 4, 1, 2, 3, 4. And you notice it's making our North Korean missile shape starting here going out to the right. Now this should be good enough to get us to graph. What would happen if we had something like a negative value? What would that be like? Well, let's go ahead and pick a new coefficient. Like let's say in this case, let's do negative 1/2. Now one valuable tool and skill that we can use is we can try to visualize what is this shape supposed to look like. Well, I know that this thing is supposed to be a North Korean missile shape, and because it's negative, what we would want to do is we would want to just kind of picture it flipped over. All right, so we should have, instead of a regular missile launch, we're going to have a flipped one. All right, because we're multiplying by 1/2, instead of it getting taller faster, it's probably going to get wider faster. So let's go ahead and pick some good values that might work out for us. Let's go ahead and start with a fan favorite, 0. Negative 1/2 times the square root of 0, which is just going to be 0. So that was nice. Let's pick a different color. Let's go with this one. If we picked 1, we would eventually have to multiply it by negative 1/2 and get a decimal. Now that's not the biggest deal in the world with 1/2, but let's just go ahead just for funsies. Let's pick a number like 4. Negative 1/2 times the square root of 4, that's negative 1/2 times 2, and negative 1/2 times 2, when x is 4, it looks like y is going to be negative 1. So when I go over 1, 2, 3, 4, I'm actually supposed to go down 1. Interesting. All right, maybe 3 is not the best number to pick, because if we did pick 3, we would have to go ahead and multiply 9 by negative 1/2. Let's, for funsies, again, let's pick a number like, I don't know, 16. Negative 1/2 times the square root of 16 is the same thing as negative 1/2 times 4, which is going to be negative 2. So it looks like this guy is going to be way over here. I can't quite see the spot, but it looks like it's going to be doing this, going towards 2. All right, and it kind of looks like what we thought. Instead of a positive missile launch, it's going to be a negative missile launch, all right, because we have a negative sign. And instead of going up faster, it's going to get wider faster. The last two things for us to talk about in this lesson are actually things you guys have seen in previous lessons. Probably one of my favorite things about algebra is the fact that a lot of it's kind of repetitive and the rules kind of follow over from previous other rules. So let's go ahead and talk about how to graph a vertical translation. Vertical meaning moving up and down. If this guy right here was my parent function and I add 2 at the end, what do you expect to happen? Well, it's going to go up 2. Literally every point from the red line just moved up 2 and formed a new blue line. Alright, so that one's pretty nice and easy to work with. What about this graph for y is equal to square root of x minus 3? Well, if this red line is my parent function and I just subtracted 3 from the bottom, it looks like it's just going to move down 3. Again, notice it's following the same exact pattern. Starting from this point, it's going to go over 1 up the square root of 1. Over 4 up the square root of 4, which is 2. Over 9 up the square root of 9, which is 3. And it follows the same exact pattern. What would happen if we had an addition or subtraction sign on the inside of our grouping symbol? Well, just like previous lessons, just like previous functions, when you have an addition on the inside of our grouping symbol, it actually moves to the left. And when you have a subtraction on the inside, it's going to move to the right. So let's go ahead and get our good friend Desmos out here. Ayo Desmos, where are you at? All right. So let's go ahead and mute this dude and put this in here. Let's say I said I have square root of x, and on the inside I put plus 6. All right, it should move to the left 6. What if I change that plus to a minus? It moved to the right. This might be one last handy thing to have in your notes that might help you going forward with all of these types of functions, especially with square root functions. If you have an a value, meaning a is greater than 1, it's going to stretch the function. If it's less than 1, it's going to compress it. Stretching means it's going to get taller faster. Compressing means it's going to get kind of smushed and wider faster. On the inside of my square root, if I have a minus sign, it's going to go to the right. If I have a addition sign, it's going to move to the left. And when I add at the end, it goes up. And when I subtract at the end, it goes down. Also remember that this less than 1 thing doesn't apply to negative signs. Negative signs simply flip the function either up or down. All right, that's it for this lesson. I hope you enjoyed it. Good luck. Go get 'em.